In 1903, the Swedish chemist Svante Arrhenius received the Nobel Prize. The award was for his work on how salts dissolve into ions in water. But Arrhenius had other bigger ideas. He helped popularize a concept called panspermia. This was the idea that life didn't start on Earth. It arrived from space. He imagined tiny microscopic spores drifting between the stars, pushed along by the gentle pressure of starlight itself. These spores would travel for millions of years, dormant and frozen. If they landed on a warm, wet planet like a young Earth, they would awaken. This life would begin. He wrote a book in 1908 called Worlds in the Making. He laid out his vision of a universe teeming with the seeds of life, scattering from one planet to another. At the time, it was a radical thought. Most people believed life was a unique miracle that happened only here. Arrhenius suggested the universe was a garden, and we were just one of the plants that grew from a seed that blew in on the cosmic wind. The idea wasn't entirely new. A Greek philosopher named Anaxagoras had thought of something similar thousands of years earlier. But Arrhenius, a Nobel laureate scientist, gave it a modern scientific footing. He made it something people could seriously consider. His work tapped into a deep human question. Are we alone? The idea of panspermia offered one answer. It said that not only are we not alone, but we might be related to life on other worlds, all born from the same cosmic ancestry. This idea that life could travel the void is a cousin to another idea. If life is out there, maybe it's not just microscopic. Maybe it's intelligent, and if it's intelligent, maybe it's trying to talk. This is the story of what happens when we listen. Number 18, the signal that came from the kitchen. The signal was perfect. It was, a short, sharp blast of radio waves lasting just a few milliseconds. It flashed across a huge range of frequencies, but the lower frequencies arrived slightly later than the higher ones. This delay, called a dispersion measure, was a crucial clue. It meant the signal had traveled a very long way through the thin plasma of interstellar space. The amount of delay suggested it came from outside our own Milky Way galaxy from a distance of billions of light years. The energy in that brief flash was immense, equal to what our sun releases in an entire day. Astronomers at the Parkes Observatory in Australia had found something big. The first of these signals was spotted in 2007, but in archived data from 2001. It was so strange and powerful it was named the Lorimer Burst after its discoverer. Soon, other telescopes started looking for similar events, and Parkes kept finding them. They called these mysterious signals peritons, named after a mythical winged stag. 2011 and 2014, the observatory detected over a dozen of them. There was a problem, though. The peritons were a little too perfect, and they had some weird habits. For one, they seemed to be detected across the entire telescope receiver, not from a single point in the sky like a real cosmic signal should be. This suggested the source might be close by, very close by. Another strange clue emerged when a student, Emily Petroff, analyzed the arrival times. The signals only seemed to happen during office hours, Monday through Friday. They rarely, if ever, appeared at night or on weekends. This was deeply suspicious. The universe doesn't care about a 9-to-5 work schedule. This pointed even more strongly to a source on Earth, what astronomers call radio frequency interference, or RFI. The hunt was on. The team at Parkes was determined to find the culprit. They knew RFI was a constant battle. The world is awash in radio waves from cell phones, Wi-Fi, television broadcasts, and countless other devices. A radio telescope is like a giant, sensitive ear, and it hears all of it, distinguishing a faint whisper from a distant galaxy from the shout of a local radio station is the daily work of a radio astronomer. They installed a new monitoring system that could pinpoint interference in real time. They waited. Then, in early 2015, they got a hit. A periton was detected. But this time, the new system also detected a strong spike of radio waves at a very specific frequency, 2.4 gigahertz. That frequency is familiar to all of us. It's the frequency used by Wi-Fi and Bluetooth. It's also the frequency used by microwave ovens. The team looked around the observatory. There were 2 microwave ovens in the staff facilities, one in a kitchen and one in a break room, both just a few hundred feet from the giant dish of the telescope. Could it be? The astronomers, people used to pondering the fate of galaxies, turned their attention to the kitchen appliances. They set up an experiment. They put a mug of water in one of the microwaves and started it. Nothing happened. The telescope detected no signal. This was confusing. The ovens were old and their shielding was likely not perfect, but they shouldn't be broadcasting signals that could be mistaken for an extragalactic event. Then someone had an idea. What if you don't wait for the timer to finish? What if you stop it early by opening the door? An engineer on the team tried it. He started the microwave and then a few seconds later pulled the door open. Instantly, the monitoring equipment screamed. A powerful, short burst of radio waves erupted from the oven. The signal had all the characteristics of a periton. It was a short, broadband burst. It even had the fake dispersion that made it look like it had traveled through space. This happened because the shutdown process of the microwave's magnetron, the device that generates the microwaves, was not instantaneous. It created a radio splash that the telescope picked up. The mystery was solved. For 17 years, astronomers had been chasing a ghost. The powerful cosmic signals from billions of light years away were actually coming from people heating up their lunch. You know, the reason it only happened during the day was because that's when people were at the observatory using the kitchen. The impatience of a hungry astronomer opening the microwave door a second too early was creating a perfect mimic of a signal from deep space. The story of the peritons is not a failure. It's a crucial lesson in science. It shows how difficult the search for new phenomena can be. It highlights the absolute necessity of ruling out all possible terrestrial explanations before claiming a cosmic discovery. Frustrating and slightly embarrassing end to the mystery, but it cleared the way for the real discoveries to come. By identifying and eliminating the fake signals, the astronomers at Parcas could now be more confident that when they saw a similar burst, it was the real deal. The hunt for the microwave ghost had made them better hunters of cosmic monsters. Number 17, the billion horsepower beam pointed at Earth. The star is almost a twin of our sun. It's about the same size, the same temperature, and the same age. It sits 94 light-years away in the constellation of Hercules. The star, named HD 164,595, is known to have at least one planet, a massive world the size of Neptune that orbits its sun in just 40 days. On May 15, 2015, a team of Russian astronomers pointed the massive Raton 600 radio telescope towards this unremarkable star system. What they heard was anything but unremarkable. They detected a single intense spike of radio waves. It was a powerful narrow band signal at a frequency of 11 gigahertz. It lasted for only 2 seconds, and then it was gone. The signal was incredibly strong. If it were a natural phenomenon, like a flare from the star, it would have been accompanied by other signs, like X-rays. There were none. If it was an artificial signal, the implications were staggering. Let's assume a civilization around HD 164,595 wanted to send a message. They could send it in all directions at once, like a light bulb. This is called an isotropic beacon. To be heard from 94 light-years away with the strength detected by Rattan 600, that beacon would require a mind-boggling amount of power. The calculation showed it would need about 100 billion watts. That is more energy than all of humanity currently produces. It's more energy than is captured by the entire Earth from the sun. A civilization capable of wielding that much power for a single broadcast would be far, far more advanced than us. But there is another possibility. Maybe they weren't broadcasting in all directions. Maybe they sent a narrow, focused beam like a laser. If they happened to aim that beam directly at Earth, the power requirements would be much, much lower. It would still be immense, equivalent to the output of a large terrestrial power plant, but it would be within the realm of what a technologically advanced society might manage. The problem is, why would they aim it directly at us? And how would they know we were here to listen? The discovery of the signal was not announced immediately. The astronomers who found it were cautious. They knew they needed to verify it. They observed the star again, but they found nothing. The signal did not repeat. For over a year, the finding remained within a small circle of researchers. Then, in August 2016, a document describing the signal was circulated among scientists preparing for a conference. It was picked up by an author and astronomer, Paul Gilster, who wrote about it on his blog. The news exploded. A signal from sun-like star could be aliens was the headline around the world. The SETI search for extraterrestrial intelligence community mobilized. The Allen Telescope Array in California and the Boquete Optical SETI Observatory in Panama quickly aimed their instruments at HD 164,595. They listened for days. They found nothing but silence. The lack of a repeating signal was a major blow to the idea that it was an intentional message. Why send a single 2-second pulse and then go quiet? Skepticism grew within the scientific community. The original Russian team themselves urged caution. They pointed out that the signal was only detected in one of the telescope's receivers, not multiple, which is a standard way to confirm a signal is real and not just a glitch. They also acknowledged that the most likely explanation was terrestrial interference. A military satellite passing through the telescope's field of view could have produced a similar signal. The 11 GHz frequency is used for various satellite communications. This is a common problem for radio telescopes. The sky is full of our own signals, so where does that leave the mystery of HD 164,595? The signal remains a one-time event. It has never been repeated. It has never been explained. The most probable answer is that it was a satellite, a piece of space debris, or some other form of man-made interference that perfectly mimicked what we might expect an alien signal to look like. It's a false positive that teaches a valuable lesson about the need for confirmation. But there is always that small, nagging possibility, what if it wasn't a satellite? What if it was a focused beam and we just happened to be in its path for a fleeting 2 seconds? What if the power required wasn't a problem for the civilization that sent it? The signal from HD 164,595 is a perfect example of a tantalizing clue that leads to a dead end. It's a single data point in a vast universe of silence, a whisper that might have been the wind. But it was enough to make us lean in and listen just a little bit closer. Number 16, The Ghost in the Galactic Center. For months, it played a cosmic game of hide and seek. An invisible object near the heart of our galaxy would suddenly flare into view, becoming one of the brightest things in the radio sky. Then, just as mysteriously, it would vanish. It happened again and again. The source, nicknamed The Ghost, was unlike anything astronomers had ever seen. The light from it was highly polarized. This means the light waves were all vibrating in the same direction, a sign that the source was located in a powerful, organized magnetic field. It would brighten and fade erratically, sometimes over a few weeks, sometimes in a single day. And when astronomers looked for it in other wavelengths, like infrared, optical, or X-ray, they found nothing. It was completely invisible except at radio frequencies. This strange object was discovered by a PhD student, Zhaiteng Wang, at the University of Sydney. He was looking at data from the Australian Square Kilometre Array Pathfinder ASCAP, one of the most powerful radio telescopes in the world. He was surveying the region around the galactic center when he noticed a source that was there in one observation and gone in the next. At first, he thought it might be a pulsar, the rapidly spinning corpse of a massive star. Pulsars emit beams of radio waves that sweep across space like a lighthouse beam. But the ghost signal was too slow and too erratic to be a normal pulsar. He considered a flaring star. But stars that flare in radio waves also tend to flare brightly in X-rays, and this object was silent in the X-ray spectrum. Wang and his team kept watching. Between 2019 and 2021, they caught the object officially named ASCAP J173608, 321,635, flaring a total of 17 times. Its behavior was baffling. It didn't fit into any existing category of astronomical object. The team searched through archival data from other telescopes looking for signs of the ghost in the past. They found it. The Parkes telescope in Australia had picked it up in 2010. The Very Large Array in the United States had seen it in 2002, 1999, and 1994. The object had been flaring on and off for at least 30 years, but because the flashes were so unpredictable, no one had ever put the pieces together. It was a long-term mystery hiding in plain sight. The polarization of the signal was one of the most important clues. The light was not just polarized, it was circularly polarized. This is much rarer than the more common linear polarization. In circularly polarized light, the orientation of the light wave spirals as it travels. This kind of polarization is usually associated with objects that have extremely strong magnetic fields, like pulsars or magnetars. But the ghost didn't behave like either of those. Another clue was its location. It was near the galactic center, a crowded and chaotic neighborhood full of massive stars, black holes, and strong magnetic fields. This is a region where strange things can happen. The astronomers considered a range of possibilities, some more exotic than others. Could it be a special type of star called a GSRT or galactic center radio transient? A few of these have been found, and they are also mysterious radio sources that flare and disappear. The ghost shared some characteristics with them, but it was also different in key ways. Could it be a pair of stars orbiting each other, their magnetic fields interacting and causing bursts of radio waves? It's possible, but there's no evidence of a companion star. The team even considered the most outlandish idea: could it be a signal from an advanced civilization? An alien beacon turning on and off? It's highly unlikely. The signal is broadband, meaning it's spread across a wide range of frequencies. An intelligent signal would probably be narrowband, focused on a single frequency to be more efficient. The mystery deepened in 2021. After flaring multiple times, the ghost simply switched off. Astronomers have been watching the spot in the sky ever since, but it has remained stubbornly silent. They don't know if it will ever turn back on. The leading hypothesis right now is that it represents a new class of celestial object. It might be related to magnetars, neutron stars with unimaginably strong magnetic fields, but a version that behaves in a way we haven't seen before. Or it could be something else entirely, something our current theories of astrophysics can't yet explain. The ghost is a reminder that the universe is still full of surprises, even in our own galaxy, in a region we have studied for decades. There are objects that defy our understanding. For now, all astronomers can do is wait and watch the place where the ghost was last seen, hoping that one day it will flicker back to life and give up more of its secrets. Number 15, the pulsar that was mistaken for little green men. In the summer of 1967, a young graduate student named Jocelyn Bell was working at the Mullard Radio Astronomy Observatory in Cambridge, England. She was part of a team led by Anthony Hewish that had just built a new kind of radio telescope. It was a sprawling array of wires and poles covering more than 4 acres, designed to study the twinkling of distant radio sources called quasars. Bell's job was to analyze the miles of paper charts that poured out of the telescope's receiver each day. It was tedious, painstaking work. She would scan the wiggly lines of ink, looking for the telltale flicker of a quasar. But in August, she found something else. It was a tiny, faint signal, just a quarter of an inch of scruffy ink on the chart paper. It didn't look like a twinkling quasar, and it didn't look like terrestrial interference. It was something new. She saw it again a month later. It was a series of sharp, regular pulses. They were incredibly fast and incredibly precise. The pulses came every 1.33730208831 seconds. This level of regularity was unheard of. Nothing in nature was known to be that precise. Bell brought the signal to Hewish's attention. He was initially skeptical, thinking it must be interference from some man-made source. But Bell was persistent. She had checked everything. It wasn't a car's ignition system. It wasn't a faulty piece of equipment. The signal was coming from a specific point in the sky that moved with the stars. It was coming from space. The team started studying the signal in secret. The regularity was so perfect that they couldn't imagine a natural explanation. Could it be a satellite? They calculated the Doppler shift, the change in frequency caused by a moving object. The signal showed no such shift. It wasn't in orbit around the Earth. So what was it? In the strained, serious atmosphere of the observatory, they started to half-jokingly consider the most extraordinary possibility. What if it was a signal from an intelligent civilization, a beacon, a clock, a message? They nicknamed the source LGM-1 for Little Green Men. It sounds fanciful now, but at the time, it was a genuine, if remote, possibility they had to consider. Hewish was worried. If it was an alien signal, how should they announce it? It would be one of the most profound discoveries in human history. The responsibility was immense. As they continued to observe LGM-1, Jocelyn Bell went back to her chart papers. And then she found another one. She found a second source of pulsing signals coming from a completely different part of the sky. It had a different pulse rate, about 1.2 seconds. This discovery was a huge relief. It was one thing to imagine a single alien civilization sending a beacon. It was much harder to believe that two different alien civilizations were sending similar beacons and that we had just happened to point our new telescope at both of them. The discovery of the second source made it much more likely that they had found a new class of natural object. Soon, they found a third and then a fourth. The Little Green Men hypothesis was dead. They had stumbled upon something far more interesting, a new kind of star. In February 1968, the team published their discovery. They called the new objects pulsars, short for pulsating radio sources. The question now was, what were they? The answer came from the theorists. The pulses were so fast and regular that the object emitting them had to be very small and very dense. A normal star would fly apart if it spun that fast. The only thing that fit the description was a neutron star. A neutron star is the collapsed core of a massive star that has exploded as a supernova. It's a city-sized ball of neutrons so dense that a single teaspoon of its material would weigh billions of tons on Earth. These objects spin incredibly fast, a consequence of conserving angular momentum from their parent star. They also have incredibly powerful magnetic fields. These fields create beams of radio waves that shoot out from the star's magnetic poles. As the star spins, these beams sweep across space. If one of the beams happens to sweep across the Earth, we see a regular pulse of radio waves. It's a cosmic lighthouse. The discovery of pulsars was a landmark moment in astronomy. It confirmed the existence of neutron stars, which had been predicted decades earlier but never observed. It opened up a new field of physics, the study of matter under extreme conditions. Anthony Hewish was awarded the Nobel Prize in physics in 1974 for his role in the discovery. Controversially, Jocelyn Bell, the graduate student who first found the signal and argued for its significance, was not included in the award. Despite the controversy, the story of LGM-1 is a classic example of scientific discovery. It started with a strange, unexplained signal. It led to a wild, speculative hypothesis. And through careful, systematic observation, it ended with a new and profound understanding of the universe. The Little Green Men turned out to be one of the most exotic and fascinating objects in the cosmos. Number 14, the repeating signal with a 16-day beat. Most mysterious radio signals from space are one-and-done events. A single, powerful flash appears out of the darkness and then vanishes forever. These are called fast radio bursts, or FRBs. For years, astronomers thought all FRBs behaved this way. Then they found FRB 121,102, a source that flashed repeatedly, proving that at least some of these events could be caused by an object that survived the outburst. But even that repeater was unpredictable. It would go through periods of frantic activity and then long stretches of silence. Then, in 2019, astronomers found something even stranger. They found a repeater that was predictable. It had a schedule. The signal, named FRB 180,916, J158 plus 65, was first detected by the CHIME radio telescope in Canada. CHIME is a revolutionary instrument. It has no moving parts. It's a set of giant stationary half pipes that look like a skateboard park for giants. It scans the sky as the Earth turns. It's exceptionally good at finding FRBs, detecting thousands of them. When the team looked at the data for FRB 180,916, they noticed a pattern. The source wasn't just repeating, it was repeating on a strict 16.35-day cycle. For a period of about 4 days, the source would produce bursts of radio waves. It might send out 1 or 2 bursts or a dozen. Then, for the next 12 days, it would go completely silent. Then, the cycle would repeat, a 4-day window of activity, followed by a 12-day window of silence, over and over again like clockwork. This was a groundbreaking discovery. It was the first time any FRB had been shown to have a periodic pattern. This periodicity was a massive clue to what might be causing it. The 16-day cycle was too slow to be the rotation period of a single object like a neutron star. A neutron star that spun that slowly wouldn't have enough energy to produce these powerful bursts. So the cause had to be something else. The astronomers came up with several theories to explain the strange rhythmic beat of this cosmic drum. One leading idea is that the FRB source is in a binary system. It could be a neutron star orbiting another star, or perhaps a black hole. In this scenario, the neutron star is always producing bursts, but we only see them for a 4-day window when our line of sight is clear. For the other 12 days, our view might be blocked by the companion star itself, or by a thick wind of gas and plasma blowing off the companion. As the neutron star moves through its orbit, it comes out from behind this obstruction, and we can see the bursts again. The 16.35-day cycle would be the orbital period of the two objects. Another possibility involves a single isolated object. It could be a young, highly magnetized neutron star known as a magnetar. These objects are known to have wobbles in their rotation, a phenomenon called precession. The Earth does something similar. Its axis of rotation slowly wobbles over a period of 26,000 years. If the magnetar's radio beam is tied to its axis, and that axis is wobbling with a 16-day period, it could cause the beam to sweep in and out of our line of sight, creating the observed pattern of activity and silence. A third, more exotic theory suggests the source could be a flarer, a magnetar that is so active it creates a thick cloud of plasma around itself. This plasma could trap the radio waves, only releasing them periodically. The 16-day cycle could be related to the time it takes for this plasma environment to build up and then dissipate. To figure out which of these theories is correct, astronomers needed more data. They traced the signal's origin to a galaxy about 500 million light-years away. That might sound far, but for an FRB, it's practically next door. The galaxy is a spiral galaxy, similar to our own Milky Way, and the FRB source is located in a star-forming region of that galaxy, a nursery where new stars are being born. This is an important clue because magnetars are thought to be formed from the collapse of massive, short-lived stars, the kind of stars found in these regions. The discovery of FRB 180,916's periodic nature transformed the study of these mysterious signals. It proved that at least some of them are not random cataclysmic events, but are produced by stable, long-lived systems. The 16-day cycle is a puzzle box. It gives theorists a set of constraints they have to work with. Any successful model for this FRB must explain not just the bursts themselves, but also the strict repeating schedule they follow. The signal is a metronome ticking hundreds of millions of light years away, and by studying its rhythm, astronomers hope to finally understand the nature of the strange engine that powers these cosmic lighthouses. Number 13, the Whispers from a Quiet Red Dwarf. Ross 128 is a small, dim star just 11 light years from Earth. It's a red dwarf, the most common type of star in our galaxy. These stars are cool and long-lived and are considered by many astronomers to be prime locations to search for habitable planets. In 2017, the star was known to have at least one planet, Ross 128b. An Earth-sized world that orbits in the star's habitable zone, the region where liquid water could exist on its surface. On May 12, 2017, astronomers at the Arecibo Observatory in Puerto Rico were observing Ross 128 as part of a survey of nearby red dwarfs. They were listening for any unusual radio signals, and they found some for a period of about 10 minutes. The giant radio telescope picked up a series of strange broadband signals coming from the direction of the star. The signals were quasi-periodic, meaning they had a sort of repeating pattern, but not a perfectly regular one. And they showed a strong dispersion, a smearing of the signal that suggested it had traveled through space. But the amount of dispersion was strange. It was high, but not high enough to suggest a source from far away. It was more consistent with a source within our solar system, or perhaps very close to the star itself. Abel Mendez, the lead astronomer on the project, was puzzled. He had never seen anything like it. Red dwarfs are known to be flary, meaning they can have sudden, violent outbursts of energy. These flares can produce radio waves, but the signals from Ross 128 didn't look like a typical stellar flare. Your flares usually produce signals at low frequencies. These signals were at high frequencies. Also, Ross 128 is known to be a particularly quiet red dwarf with very little flare activity. The team considered other possibilities. Could it be interference? Arecibo is a sensitive instrument and it often picks up man-made signals. But the signal had a dispersion feature, which is very hard for terrestrial interference to mimic. Mendez and his team decided to observe the star again. They listened for an hour, but heard nothing. The signal was gone. Faced with this strange, non-repeating signal, Mendez decided to do something unusual. He wrote a blog post about it. He laid out all the data and the different possibilities from the mundane to the extraordinary. He listed the three most likely explanations. First, it could be an unusual type of stellar flare from Ross 128. Second, it could be emissions from some other object in the field of view of the telescope. Or third, it could be a burst from a high-orbit satellite. He knew that by going public, he was opening the door to wild speculation. He even mentioned, at the very end of his list of possibilities, the aliens hypothesis, though he was quick to state that it was the least likely explanation. The media, of course, seized on that last possibility, the story of a strange signal from a nearby star with a potentially habitable planet was irresistible. The headlines were full of talk of aliens. The SETI Institute in California quickly organized a follow-up observation campaign using both the Allen Telescope Array and the Green Bank Telescope. They pointed their telescopes at Ross 128 and listened. The results came back quickly. They found nothing. There were no signals at the frequencies observed by Arecibo. The silence from the SETI telescopes was a strong indication that the signal was not an extraterrestrial communication. An intelligent signal would likely be broadcast continuously, not as a single 10-minute burst. The solution to the mystery came a few days later. After analyzing data from other radio telescopes that were looking at different parts of the sky at the same time, the team was able to triangulate the source. The signal was not coming from Ross 128, it was coming from one or more geostationary satellites. These are communication satellites that orbit the Earth at an altitude of about 22,000 miles. They are so far away that their signals, when picked up by a sensitive telescope like Arecibo, can exhibit a dispersion-like effect that mimics a signal from space. The satellites were broadcasting in a frequency band close to the one the astronomers were observing. The strange, quasi-periodic nature of the signal was likely due to the A combination of signals from multiple satellites interfering with each other. The Ross 128 signal was a case of mistaken identity. It was a ghost in the machine, a reflection of our own technology that we briefly mistook for a voice from the stars. The incident was a powerful reminder of how hard it is to do radio astronomy in a world that is saturated with our own radio transmissions. Every time we build a more sensitive telescope, we also get better at detecting the noise from our own civilization. For the astronomers at Arecibo, it was a valuable, if slightly disappointing experience. They had followed the scientific method, and it had led them to the right answer. The whispers from Ross 128 were not from an alien world, they were from our own. Number 12, the signal that defied explanation for 30 years. In the late 1970s, a French astronomer named Gilles Chirac was working on his PhD thesis. He was using a radio telescope in Nankai, France, to study the hydrogen gas in nearby galaxies. Hydrogen is the most abundant element in the universe, and it emits a faint radio signal at a very specific frequency, 1420 megahertz. This hydrogen line is a fundamental frequency of nature. Some SETI researchers have argued that if an alien civilization wanted to send a message, they might use this frequency, as it would be a universal standard that any technological society would know about. Chiraki was not looking for aliens. He was just trying to map the gas in galaxies. But he found something that he couldn't explain. He was looking at data from a galaxy called M33. As he was analyzing the signals, he noticed a strange, narrow band signal that seemed to be coming from a point just outside the galaxy. It was a strong, clear signal, but it didn't look like the normal, broad signal from hydrogen gas. And it was shifting in frequency over time. This Doppler drift is what you get from an object that is accelerating or decelerating relative to the observer. The signal appeared, drifted in frequency for a while, and then disappeared. Chiraki noted it in his logbook, but he couldn't explain it. It was an anomaly in his data, and he set it aside to focus on his main research. The years passed. In the 1990s, the SETI Institute launched Project Phoenix, one of the most ambitious searches for extraterrestrial intelligence ever undertaken. They were systematically scanning the nearest 1,000 sun-like stars, listening for narrow band signals that could be a sign of technology. As part of their project, they developed sophisticated software to automatically detect and flag these kinds of signals. They also went back and reanalyzed old data from other radio astronomy projects looking for missed signals. They got a copy of the old Nankai telescope data from the 1980s. When they ran it through their new software, it flagged a signal. It was the same strange drifting signal that Gilles Chiraki had seen years before. The SETI team was intrigued. The signal had all the hallmarks of a potential candidate. It was narrowband, which is a sign of an artificial transmitter. It had a Doppler drift, which could mean it was coming from a planet rotating on its axis or orbiting its star. And it was a one-time event, which made it difficult to dismiss as simple interference. The team tried to track down the source. They pointed their own telescopes at the same spot in the sky where the signal had been detected. They found nothing. They searched through satellite databases to see if a satellite could have been in the telescope's beam at that exact time. They found no match. The mystery of the Nankai signal, sometimes called the French signal, persisted for decades. It was a classic wow signal, case a tantalizing, unconfirmed detection that could be anything. It was a favorite topic of discussion among SETI researchers. Was it a real signal from an alien civilization? Or was it just a particularly stubborn piece of terrestrial interference that had managed to fool everyone? The answer, when it finally came, was a little bit of both. In 2015, a team of astronomers decided to take another crack at the problem. By this time, satellite tracking data was much more comprehensive and accessible. They went back to the original date and time of the detection, and they did a much deeper search of all the objects that were in orbit at the time. And they found it. They found a culprit. It was an American satellite called LES-1. And LES-1 was a small experimental communication satellite launched in 1965. It was supposed to be in a particular orbit, but a booster rocket failed, and it was left tumbling in the wrong orbit. It was officially declared lost in 1967, but it wasn't dead. Its solar panels and transmitter were still working, at least intermittently. As it tumbled through space, its transmitter would occasionally be powered up, and it would start broadcasting. Its unstable, tumbling motion would cause its signal to drift in frequency, exactly like the signal seen at Namke. The team was able to match the satellite's predicted position with the telescope's pointing direction at the exact time of the observation. It was a perfect match. After more than 30 years, the mystery was solved. The strange, drifting signal from the direction of M33 was not from another galaxy. It was not a message from an alien civilization. It was the ghost of a failed Cold War-era satellite, still muttering to itself as it tumbled through the darkness of space. The story of the Namke signal is a perfect illustration of the challenges of SETI. The universe is a noisy place, but most of the noise is our own. Finding a true alien signal is like trying to hear a pin drop in the middle of a rock concert. It requires incredible patience, skepticism, and a willingness to chase down every possible source of interference, no matter how obscure. The French signal wasn't ET, but solving its mystery was a testament to the detective work that is at the heart of the scientific search. It's number 11, the star that dimmed so much it looked artificial. The star is called KIC 8,462,852, but most people know it as Tabby's star, named after Tabitha Boyajian, the astronomer who led the team that first studied its strange behavior. It's a fairly ordinary star, a little bigger and hotter than our sun, located about 1,500 light-years away in the constellation Cygnus. In 2015, it became the most famous star in the galaxy. The Kepler Space Telescope had been staring at it, along with 150,000 other stars, for 4 years. Kepler's job was to look for tiny, regular dips in starlight, the telltale sign of a planet passing in front of its star. But the dips from Tabby's star were anything but tiny or regular. The star was dimming by incredible amounts. A Jupiter-sized planet, the largest in our solar system, would cause a star like this to dim by about 1%. The dips from Tabby's star were reaching 15%, and one of them was a staggering 22%. This meant that something was blocking out a fifth of the star's light. Whatever it was, it had to be huge. And the pattern was chaotic. There were small dips and huge dips. They lasted for days or weeks. They followed no predictable schedule. It was unlike anything astronomers had ever seen. The data was so weird that at first the scientists thought it was a mistake, a flaw in the telescope or the data processing, but they checked and rechecked. The signal was real. The team published a paper describing the bizarre light curve of the star. They considered a range of natural explanations. Could it be a swarm of comets? A huge group of comets breaking up as they passed close to the star could create a cloud of dust and debris that could block the light. This was their leading natural hypothesis, but the amount of dust required would be enormous. It would take hundreds of thousands of giant comets to produce the observed dimming. It's not impossible, but it would be an extraordinary and unprecedented event. Could it be a planetary collision? Two massive planets smashing into each other would create a massive cloud of debris. But this cloud would be hot, and it would glow in infrared light. When astronomers looked at Tabby's star with infrared telescopes, they didn't see the expected glow. With the natural explanations all having serious problems, some astronomers began to consider a more radical idea. Jason Wright, an astronomer at Penn State University, was one of them. He pointed out that the strange light curve was consistent with what you might expect to see from a massive artificial structure orbiting the star. He was talking about a Dyson swarm, a hypothetical megastructure that an advanced civilization might build to capture energy from its star. This idea, originally proposed by the physicist Freeman Dyson, imagines a civilization building a vast number of solar collectors and habitats in orbit, eventually surrounding the star. Such a structure wouldn't be a solid shell, but a dense swarm of objects. As this swarm orbited, it would block the starlight in a complex, irregular way, just like what was being observed at Tabby's star. This was a sensational idea, and it captured the public's imagination. The media dubbed Tabby's star the alien megastructure star. It was a thrilling possibility, but the scientists involved were extremely cautious. They stressed that the artificial hypothesis was a last resort. Before you can claim something as aliens, you have to rule out every single possible natural explanation. The SETI Institute pointed its radio telescopes at the star, listening for any signals that might be a sign of technology. They found nothing. A crowdfunding campaign raised over $100,000 to buy more telescope time to continuously monitor the star. Over the next few years, a global network of professional and amateur astronomers kept a close watch on Tabby's star. They observed it in every wavelength of light, and slowly, a new picture began to emerge. They found that different colors of light were blocked by different amounts. Blue light was blocked more than red light. This is a crucial clue. A solid, opaque object, like a piece of an alien megastructure, would block all colors of light equally. But very fine dust particles will scatter blue light more than red light. It's the same reason the sky is blue on Earth. The new data strongly pointed towards dust as the culprit. The leading theory now is not comets, but circumstellar dust. The idea is that the star is surrounded by a cloud of fine dust particles. The dimming events are not caused by a single large object, but by thicker clumps of this dust passing in front of the star. But where did the dust come from? That's still a mystery. It could be from a planet that was destroyed, or from a group of comets or asteroids that collided. Or the star itself might have some unusual properties that are causing it to shed dust. The alien megastructure hypothesis has largely been abandoned by the scientific community. The evidence for dust is just too strong, but Tabby's star remains a fascinating and important object. It showed us a new way that stars can behave. It challenged our assumptions and forced astronomers to think creatively. And for a brief, exciting moment, it made us confront the possibility that we are not the only builders in the universe. It was a false alarm, but it was a magnificent one. Number 10, the CTA 102 blip that became a folk song. In 1964, the world was in the grip of the Cold War and the space race. The Beatles were invading America, and astronomers were just beginning to grapple with the discovery of bizarre new objects called quasars. These were star-like points of light that were incredibly bright and incredibly far away, pouring out more energy than entire galaxies. Their nature was a complete mystery. At the Palomar Observatory in California, astronomers were studying the radio emissions from these strange objects. In the spring of that year, a team of Russian astronomers, led by Nikolai Kardashev, made a startling announcement. They had been observing a quasar called CTA 102, and they had found something strange about its radio signal. Kardashev claimed that the signal from CTA 102 was varying in a regular periodic way. He suggested that this periodic variation could be a sign of an artificial signal. He was the creator of the Kardashev scale, a method of classifying advanced civilizations based on their energy consumption. A Type 1 civilization could harness all the energy of its planet. A Type the Second could harness all the energy of its star. A Type the Third could harness the energy of its entire galaxy. Kardashev's suggestion was that CTA-102 could be a beacon from a Type the Second or Type the Third civilization. The news was reported by the official Soviet news agency TASS. It caused an immediate sensation around the world. For a few frantic weeks, it seemed like humanity might be on the verge of its first contact with an extraterrestrial intelligence. The timing of the announcement was significant. The US and the Soviet Union were locked in a fierce competition for technological and ideological supremacy. A discovery like this would be a massive propaganda victory for whichever side made it. Western astronomers were skeptical. They had also been observing CTA-102, and they hadn't seen any evidence of a periodic signal. They rushed to their telescopes to re-observe the object. The American astronomer Martin Schmidt, who had been the first to correctly identify the nature of quasars, publicly expressed his doubts. He argued that it was far more likely that the Russians had either made a mistake in their analysis or that they were misinterpreting natural variations. The mystery deepened when American journalists tried to get more information from the Russian team. A group of reporters gathered at the Sternberg Astronomical Institute in Moscow, waiting for a press conference that had been announced. But the conference was abruptly canceled. The scientists were unavailable for comment. The official story was that they needed more time to verify their data. The speculation ran wild. Had the Kremlin silenced the astronomers? Was this a genuine discovery being covered up? Or was it all a hoax, a piece of Cold War propaganda designed to make the Soviet Union look scientifically advanced? The truth, as it often is, was more mundane. A few weeks later, the Russian team quietly retracted their claim. They announced that further observations had not confirmed the initial finding of a periodic signal. The variations they had seen were likely just random fluctuations, the natural winkling of a distant radio source. The great alien signal from CTA-102 was a false alarm, but the story didn't end there. The brief, intense flurry of excitement had captured the public imagination. In 1965, a new American folk rock band called The Byrds was looking for material for their second album. The band's leader, Roger McGuinn, was fascinated by science fiction and the idea of extraterrestrial life. He and his bandmate, Chris Hillman, decided to write a song about the CTA-102 incident. The song, simply called TTA-102, was a strange atmospheric piece of music. It featured a spoken word introduction by the band's producer and sound effects meant to evoke the sounds of space. The lyrics were a cryptic and playful take on the idea of receiving a message from aliens. The song was never a hit, but it became a cult favorite. It was a piece of pop culture ephemera that captured the strange mix of scientific curiosity, Cold War paranoia, and hopeful optimism of the era. The story of CTA-102 is a fascinating footnote in the history of SETI. The initial claim was almost certainly a mistake, perhaps amplified by a desire to make a big splash on the world stage. It's a cautionary tale about the dangers of jumping to conclusions and the need for rigorous verification in science. But it's also a story about the power of an idea. For a few short weeks, the world looked up at a faint point of light in the sky and dared to imagine that someone was waving back. And that idea was so powerful that it was set to music, a strange and wonderful legacy for a signal that never really was. Number 9, the weird signal from the Arecibo telescope. On November 16, 1974, a group of astronomers gathered at the Arecibo Observatory in Puerto Rico to celebrate a major upgrade to the giant radio telescope. To mark the occasion, they decided to do something symbolic. They would use the newly powerful telescope to broadcast a message into space. The message, designed by Frank Drake and Carl Sagan, was a simple pictorial message aimed at a star cluster called M13, about 25,000 light-years away. It was a greeting card from humanity, a digital "we were here." It was a broadcast, not a search. But Arecibo's main job was to listen. For decades, it was the world's most sensitive ear, listening for the faint whispers of the cosmos. And sometimes, it heard things it couldn't explain. One of the most intriguing came from the SETI Home project. And launched in 1999, SETI Home was a revolutionary idea. It used the idle processing power of millions of personal computers around the world to analyze the vast amounts of data collected by the Arecibo telescope. It was a way for anyone with a computer to participate in the search for extraterrestrial intelligence. The software would sift through the noise, looking for narrow band signals that stood out. Over the years, the project identified hundreds of promising candidate signals. Most of these were quickly dismissed as terrestrial interference or satellite noise. But a few were more persistent. The most famous of these was a signal designated SHGB02. The signal was first detected on March 1st, 2003. It was a faint narrow band signal at a frequency of about 1420 megahertz. This was significant. 1420 MHz is the hydrogen line, the frequency at which neutral hydrogen atoms emit radio waves. As mentioned before, some scientists believe this would be a natural calling card frequency for any civilization to use. The signal was observed a total of 3 times, for about a minute each time. This was also significant. A signal that repeats is much more likely to be real than a one-time blip. But the most intriguing thing about SHGB02 plus 14 was its drift rate. The signal was rapidly changing in frequency, drifting at a rate of about 8 to 37 hertz per second. This rapid Doppler drift is what you would expect from a transmitter on a planet that is rotating very, very fast. The calculations showed that the source would have to be on a planet spinning about 40 times faster than Earth. A day on this planet would last less than an hour. A person standing on its equator would be moving at nearly 40,000 miles per hour, close to the planet's escape velocity. They would be on the verge of being thrown off into space. This seemed highly unlikely. A planet spinning that fast would likely tear itself apart. The signal's location was also a puzzle. It seemed to be coming from a point in the sky between the constellations of Pisces and Aries. There are no major stars in that direction for hundreds of light years. This made the signal even harder to explain. If it was an alien beacon, why was it coming from the middle of nowhere? The SETI Home team was cautious. They knew that the signal had many characteristics that made it a good candidate, but also several that were deeply strange. The rapid drift was the biggest problem. No known natural phenomenon could explain it. And the idea of a planet spinning that fast was physically implausible. The team pointed the Arecibo telescope back at the same spot in the sky to try and find the signal again. They listened for hours, they found nothing, the signal had vanished. This is the great frustration of SETI. A signal must be repeatable to be considered credible. A one-time detection, no matter how intriguing, is just an anomaly. So what was SHGB02 plus 14? The truth is, we still don't know for sure. The most likely explanation is that it was a particularly clever and elusive form of man-made interference. Perhaps it was a previously unknown type of satellite behavior, or a reflection of a terrestrial signal off a piece of space debris. The rapid drift could have been caused by the motion of the interfering source, but there is no definitive proof. The signal remains one of the best unsolved cases in the files of SETI Home. It's a data point that doesn't quite fit. The project's leaders have stated that while it's their best candidate signal to date, the probability of it being a real ETI signal is still very low. The story of SHGB0214A is a perfect example of the needle in a haystack nature of the search. For a moment, the software found something that looked like a needle. It was the right color and shape. But when the scientists looked closer, it had some very strange properties that made it unlikely to be a real needle. And then when they tried to find it again, it was gone, the haystack is vast, and the search continues. Number 8, the slow, rhythmic pulse from a cosmic anomaly. The universe has a rhythm. Stars pulse, galaxies rotate, planets orbit. But most of these rhythms are either very fast, like the millisecond pulses of a neutron star, or very slow, like the 230 million year orbit of our sun around the galactic center. In 2020, astronomers found something new. They found a cosmic object that was blinking on a human timescale. It was sending out a powerful beam of radio waves every 18.6 minutes. For 1 minute, it would be one of the brightest radio sources in the sky. Then, for the next 17.5 minutes, it would be completely silent. This was a rhythm that no known object should have. The object, named Gleam X J162059 at 523,504.3, was discovered by a student at Curtin University in Australia, Tyrone O'Doherty. And he was analyzing data from the Murchison Wide Field Array, a radio telescope in the Australian outback. He found a source that was appearing and disappearing over the course of several hours. At first, the team thought it might be a glitch or interference, but when they looked back through archival data, they found that the object had been flashing regularly for at least 3 months in 2018. The signal was also highly polarized, a sign of strong magnetic fields. The 18.6-minute period was a complete puzzle. If the object was a pulsar, a spinning neutron star, it was spinning impossibly slowly. Pulsars are like cosmic spinning tops. As they age, they slow down, but the slowest known pulsar still spins once every few seconds. An 18-minute rotation period would mean the pulsar was incredibly old and should have long ago crossed the death line, the point at which its rotation is too slow to generate radio waves. It just shouldn't be possible. So, if it wasn't a pulsar, what was it? The team considered a white dwarf, the dense remnant of a sun-like star. Some white dwarfs have strong magnetic fields and spin, and they can produce radio waves. But the most powerful white dwarf pulsars are thousands of times weaker than the signal from this new object. This thing was a blowtorch, and white dwarfs are usually candles. The object was also a complete loner. It was located in a seemingly empty patch of space, with no nearby star cluster or supernova remnant to give a clue to its origin. It was about 4,000 light-years from Earth. The leading hypothesis is that the object is a new and exotic type of magnetar. A magnetar is a type of neutron star with an unbelievably powerful magnetic field, quadrillions of times stronger than Earth's. These objects are the most powerful magnets in the known universe. They are known to produce powerful bursts of energy. Perhaps this object is an ultra-long-period magnetar, a type of magnetar that has been predicted by theorists but never before seen. The idea is that its incredibly strong magnetic field is what is powering the radio emission, even though its rotation is very slow. The intense magnetic field could be twisting and snapping, releasing huge amounts of energy that we see as the radio pulse. But this theory has problems too. You know, it's not clear how a magnetar could have slowed down to an 18-minute period so quickly, or how it could maintain such a bright radio beam. The object is pushing the boundaries of our understanding of physics. It's a new kind of beast in the cosmic zoo. After its 3-month-long performance in 2018, the object switched off. It hasn't been seen since. Astronomers are now scanning the skies looking for it to turn back on and searching for other objects like it. They believe it's unlikely to be a one-of-a-kind object. There could be a whole population of these slow periodic radio sources out there hiding in plain sight. You know, we just didn't know how to look for them. The discovery of Gleam X J1659 to 523,504.3 is a perfect example of how science works. A single, unexpected discovery can open up a whole new field of research. It's a reminder that the universe is always more creative and surprising than we imagine. The slow, steady beat of this object is like a drum in the dark, signaling the existence of a new and mysterious phenomenon. For now, it is a rhythm without an explanation, a cosmic metronome ticking away the seconds of a mystery we are only just beginning to unravel. Number 7. The bizarrely repeating heartbeat burst. Most fast radio bursts are like cosmic fireflies, flashing once in the dark and then disappearing forever. Then came the repeaters, which flashed sporadically like a faulty light bulb. But in 2019, astronomers found something else, something that combined the power of an FRB with the regularity of a pulsar. They found a signal that was repeating, but not randomly. It was repeating with a bizarrely consistent rhythm, like a cosmic heartbeat. The signal FRB 2019-122A was discovered by the CHIME telescope in Canada. When astronomers looked at the individual bursts from this source, they noticed something astonishing. The bursts themselves were made up of multiple subbursts, and the time between these subbursts was almost perfectly regular, about 217 milliseconds. This was not a pattern that was supposed to exist. It was like finding a drum solo in the middle of a burst of static. The bursts were also surprisingly long, lasting up to 3 seconds. This is about 1,000 times longer than a typical FRB. And during that 3-second window, the source would pulse with the regularity of a metronome. This discovery was a game changer. It blurred the lines between two different types of cosmic objects, FRBs and pulsars. FRBs are thought to be the most powerful radio bursts in the universe, likely caused by cataclysmic events involving magnetars. Pulsars are the rapidly spinning, highly magnetized remnants of massive stars known for their clock-like regularity. This new signal seemed to be a hybrid of the two. It had the power and distance of an FRB, but the periodic rhythmic pulsing of a pulsar. The signal's origin was traced to a galaxy about 3 billion light-years away. The energy required to produce such a bright, regular signal from that distance is immense. The question is, what kind of engine could produce a signal with this much power and this much structure? The astronomers who discovered it believe the source is almost certainly a magnetar, but a very special one. The 217 millisecond periodicity is likely related to the magnetar's rotation period. But a magnetar spinning that's slowly about 5 times per second shouldn't be able to produce the kind of energy seen in the bursts. One theory is that the magnetar is interacting with a surrounding cloud of plasma. The magnetar's powerful magnetic field could be creating waves in this plasma, and these waves could be amplifying the radio signals, making them much brighter than they would normally be. The regular pulses could be the result of the magnetar's rotation chopping up this amplified signal. Another possibility is that the bursts are not from the magnetar itself, but from a starquake on its surface. Magnetars have such strong magnetic fields that they can cause the star's crust to crack and shift. These starquakes can release enormous amounts of energy. Perhaps the regular pulsing is some kind of seismic ringing of the star after a massive quake. The discovery of this heartbeat signal has opened up a new window into the physics of extreme objects. It provides a direct link between the mysterious FRBs and the better understood pulsars. It suggests that there might be a continuum of objects with pulsars on one end, normal FRBs on the other, and strange hybrid objects like this one in the middle. It also provides a new tool for probing the universe. The signal's journey to Earth was affected by the matter it passed through. By studying the subtle distortions in the signal, astronomers can learn about the distribution of matter in the vast, empty spaces between galaxies. The signal is a gift from the deep universe. It's a message, not in the sense of an intelligent communication, but in the sense that it carries a huge amount of information about the object that created it and the medium it traveled through. It's a complex, structured signal that defies simple explanation. The cosmic heartbeat is a puzzle. It's a rhythm that we're only just starting to learn the dance to. Each beat is a clue, a piece of a story about the most violent and energetic events the universe has to offer. And astronomers are listening intently for the next beat. Number 6. The cosmic yawn that lasts for minutes. Fast radio bursts are, by definition, fast. They last for a few thousandths of a second. That's their defining characteristic. But what if they weren't? What if there was a type of burst that was just as powerful, but lasted 1,000 times longer? In 2022, astronomers found just that. They discovered an FRB that lasted for a whopping 3 seconds. But it wasn't a continuous blast. It was a series of sharp rhythmic pulses, like a drum roll, that repeated every 0.2 seconds for the duration of the burst. The event was so unusual that it challenged the very definition of what an FRB is. The burst, named FRB 2022-0610, was detected by the CHIME telescope in Canada and later studied in detail by the Carl G. Jansky Very Large Array VLA in New Mexico. The VLA was able to pinpoint its location with incredible precision. It came from a galaxy about 800 million light-years away. This was a dwarf galaxy, much smaller than our Milky Way, and the source of the burst was not in the galaxy's chaotic center, but in its quiet suburbs, a region where stars are old and star formation has long since ceased. This location was a major puzzle. The leading theory for FRBs is that they are produced by young hyperactive magnetars, which are born from the collapse of massive stars. These massive stars live fast and die young, so they are almost always found in active star-forming regions. Finding an FRB in a sleepy, residential neighborhood of a galaxy was like finding a rock concert in a library. It didn't fit. The long duration and the rhythmic pulsing of the burst were also deeply strange. The astronomers who studied it called it a cosmic yawn. It was like the universe was stretching and releasing a long, slow burst of energy. The 0.2 second rhythm was too slow to be the rotation of a normal neutron star, but it was in the right ballpark for a highly magnetized one, a magnetar. The team proposed a scenario to explain the bizarre event. They suggested that the source is a magnetar, but not a young, energetic one. Instead, it could be an older magnetar that has been quiet for a long time. It could also be the result of a merger of two neutron stars. When two neutron stars collide, they can form a single, more massive neutron star that is highly magnetized and spins rapidly. This new object, called a blitzar, would be unstable and would eventually collapse into a black hole, but for a brief period, it could be a powerful source of FRBs. This merger scenario would explain the burst's location. Neutron star binaries can be kicked out of their birthplace during the supernova explosions that create them. They can travel for millions of years before they finally merge. This would give them plenty of time to wander out into the quiet suburbs of their host galaxy. The long duration of the burst could be a sign that we are seeing the afterglow of the merger, the final sputtering gasps of the newborn magnetar before it collapses. The discovery of FRB 202610 has thrown a wrench into our understanding of these cosmic explosions. It suggests that there may be multiple ways to make an FRB. The young magnetar model might explain many of them, but this new event points to a different origin story, one involving the violent collision of dead stars. It also blurs the lines between different types of astronomical events. The merger of two neutron stars is also known to produce gravitational waves and short gamma-ray bursts. Now it seems they might produce these strange long-duration FRBs as well. The cosmic yawn is a new piece in a very complex puzzle. It's a signal that doesn't fit neatly into any of our existing boxes. It's both an FRB and not an FRB. It has features of a pulsar, a magnetar, and a cataclysmic merger event all rolled into one. It's a hybrid, a chimera, a new kind of cosmic beast, and it's a reminder that every time we think we have a handle on the universe, it finds a new way to surprise us. The universe isn't just sending us postcards, it's sending us riddles, wrapped in a mystery, inside an enigma, traveling for 800 million years to land in our telescopes. And the fun is just beginning. Number 5, the very first fast radio burst. For 6 years, it was a signal that lived only on a dusty hard drive. In 2001, the Parkes Radio Telescope in Australia was conducting a survey of the Magellanic Clouds, two small galaxies that orbit our own Milky Way. The telescope scanned the sky, recording terabytes of data. That data was then archived, waiting for someone to have the time to look at it. 6 years later, a graduate student named David Narkovic was sifting through that old data. He was working with his supervisor, Duncan Lorimer. Their project had nothing to do with finding new cosmic signals. They were looking for something else entirely. But as Narkovich's computer crunched through the data, it flagged something extraordinary. On August 24th, 2001, the telescope had recorded a single, mind-bogglingly powerful burst of radio waves. It lasted for less than 5 milliseconds. It was so bright that it saturated the telescope's detectors. And it had an enormous dispersion measure. This meant that the signal had traveled an immense distance through a huge amount of interstellar and intergalactic plasma. The calculations showed that it had come from a galaxy about 3 billion light years away. In those few milliseconds, the burst had released as much energy as the sun does in a month. It was a completely new type of astronomical event. Lorimer was stunned. He was also deeply skeptical. The signal was so strange, so powerful, and so perfectly aligned with what a theoretical cosmic explosion might look like that he was sure it had to be a mistake. It was too good to be true. He and his team spent months trying to prove it was fake. They checked the telescope's logs. They looked for any possible source of interference. They considered every possibility. Was it a weather balloon, a secret military satellite, a reflection from the moon? Nothing fit. The dispersion of the signal was the smoking gun. It was a perfect textbook example of a signal that had traveled through a vast cosmic distance. It was almost impossible to fake with terrestrial technology. After exhausting every other possibility, Lorimer and his team were forced to conclude that the signal was real. It was a genuine astrophysical phenomenon. In 2007, they published their discovery in the journal Science. They called the event the Lorimer Burst, but it would soon become known as the first fast radio burst, or FRB. The discovery was met with a mix of excitement and skepticism from the wider astronomical community. Many astronomers simply didn't believe it. A single, one-off event found in archival data was not enough to convince them. They called it a one-off curiosity. The field of FRB research was born in controversy. The problem was that no one else could find one. Astronomers pointed their telescopes at the sky, looking for similar bursts, but they found nothing. For years, the Lorimer burst was a lonely anomaly. The team at Parkes kept looking. They found the perytons, the fake signals that were eventually traced to the kitchen microwave. This made other astronomers even more skeptical. If the Parkes telescope was being fooled by a microwave oven, how could they be sure the Lorimer burst wasn't just another, more subtle form of interference? The pressure was on. If FRBs were real, there had to be more of them. Then, in 2012, another one was found, this time by the Arecibo telescope. A year later, the Parkes telescope found 4 more. The floodgates had opened. It turned out that FRBs were not rare at all. They were happening all the time, all over the sky. Previous surveys had just not been looking in the right way. They were like a cosmic flash mob, brief but brilliant events that you had to be lucky to catch. The discovery of the Lorimer burst was a moment of pure serendipity. It was a combination of an old telescope, an archived piece of data, and a student who was looking for something else entirely. It's a classic story of scientific discovery. It wasn't planned. It wasn't the result of a grand theory. It was an accident. Today, thousands of FRBs have been discovered. They are one of the hottest topics in astronomy. We now know that some of them repeat. We have traced some of them back to their host galaxies. The leading theory is that most of them are caused by magnetars. But the fundamental mystery of what they are and how they are produced is still not solved. And it all started with a single 5 millisecond flash of static on an old hard drive. The Lorimer burst was the first shot fired in a new revolution in astronomy. It was the signal that opened a new window on the universe, a window that looks out onto the most energetic and mysterious events since the Big Bang itself. It was the whisper that became a roar. Number 4, the repeater that broke all the rules. 4 years, fast radio bursts were a source of immense frustration. They were ghosts. They would appear once in a brilliant flash and then vanish without a trace. It was impossible to study them in detail. You couldn't point other telescopes at the source to see if it was visible in other wavelengths. By the time you turned your telescope, the show was over. All of that changed in 2012. A graduate student named Laura Spittler was looking at data from the Arecibo radio telescope. She found an FRB. That was exciting, but not revolutionary. But then she kept looking at the same spot in the sky, and she found another one, and another, and another. She had found the first repeating FRB. The object, named FRB 121102, was a game changer. It was not a ghost. It was a living, breathing creature. It was located in a tiny dwarf galaxy about 3 billion light years away, and it was hyperactive. On some days, it would produce hundreds of bursts. On other days, it would be completely silent. Its behavior was erratic and unpredictable, but the fact that it was repeating at all was the most important clue. It meant that whatever was producing the bursts was not destroying itself in the process. This ruled out one time cataclysmic events like the merger of two neutron stars or the collapse of a star into a black hole. The engine behind FRB 121102 was a long-lived, stable object. The discovery of the repeater allowed astronomers to do something they had only dreamed of. They could study an FRB source in real time with a whole battery of telescopes across the entire electromagnetic spectrum. They pointed radio, optical, X-ray, and gamma-ray telescopes at the source and waited for it to burst. The results were fascinating. They found that the source was located in a persistent radio source, a small, compact nebula of glowing gas. This nebula was 1,000 times brighter than similar nebulae in our own galaxy. The bursts themselves were also highly polarized and had a strange twisting signature called a Faraday rotation. All of these clues pointed towards one culprit, a magnetar. The theory was that a young, extremely powerful magnetar was at the heart of the nebula. This magnetar was releasing the powerful bursts, and its energy was also powering the surrounding nebula, causing it to glow. The extreme magnetic field of the magnetar would also explain the twisting of the radio waves. This magnetar in a nebula model became the leading explanation for FRB 121102, and by extension for many other FRBs. But the repeater still had more surprises in store. As astronomers continued to monitor it, they noticed that its bursts were not all the same. They had a wide range of brightnesses and shapes, and the frequency of the bursts seemed to be drifting downwards over time. This downward drift was a puzzle. It could be a sign that the magnetar is aging and its bursts are becoming weaker and less frequent. Or it could be related to changes in the surrounding nebula. The repeater's behavior was so complex that it seemed to defy any simple explanation. It was as if it was deliberately trying to confuse us. And then, in 2020, another repeating FRB was found, the one with the 16-day cycle. This new repeater was much closer and much more predictable than FRB 121102. It seemed that not all repeaters were created equal. There might be different types of repeaters with different underlying mechanisms. FRB 121102 was the Rosetta Stone of FRB research. It was the key that unlocked the mystery of where these signals were coming from. It proved that they were extragalactic. It proved that at least some of them were from long-lived sources. And it provided a wealth of data that pointed strongly towards the magnetar model. But it also left us with a new set of mysteries. Why is its behavior so erratic? What is the nature of the surrounding nebula, and why are its bursts changing over time? The first repeater was not the end of the story. It was the beginning of a new chapter, one that is still being written. It is a cosmic puzzle box, and every time we think we have solved it, we find that there is another, more complex puzzle hidden inside. Number 3, the signal from our nearest stellar neighbor. Proxima Centauri is the closest star to our sun. It's a small, dim red dwarf just 4.2 light years away. It's part of a triple star system, along with the two brighter stars Alpha Centauri A and B. In 2016, astronomers discovered a planet orbiting Proxima Centauri. The planet, Proxima b, is slightly more massive than Earth and orbits in the star's habitable zone. This makes it one of the most intriguing targets in the search for life beyond Earth. In 2019, a project called Breakthrough Listen, a massive privately funded effort to search for extraterrestrial intelligence, was observing Proxima Centauri with the Parkes Radio Telescope in Australia. They were not expecting to find anything. It was a routine observation, but they recorded a signal that was anything but routine. The signal was discovered a year later, in 2020, by a student intern named Shane Smith. He was combing through the data when he found a narrow band signal at a frequency of 982.002 megahertz. It was a faint but persistent signal that lasted for about 3 hours. It had all the characteristics of an artificial signal. It was narrowband, which is the hallmark of technology, and it was drifting in frequency. This Doppler drift was exactly what you would expect from a signal coming from a transmitter on a planet that is rotating and orbiting its star. The drift was positive, meaning the frequency was increasing. This indicated that the source was moving towards us. The team at Breakthrough Listen was electrified. They had a wow signal moment. This was the most significant candidate signal they had found in the project's history. They nicknamed it BLC-1 for Breakthrough Listen Candidate 1. They immediately began a rigorous process of elimination. The number one rule of SETI is it's not aliens until you've ruled out everything else. And everything else is a very long list. The team spent months trying to find a terrestrial explanation for the signal. They checked every satellite database. They looked for any possible source of ground-based interference. They analyzed the telescope's own systems. The signal had some very compelling features. It was only present when the telescope was pointing at Proxima Centauri. When the telescope moved to a different target, the signal disappeared. When it moved back, the signal was there again. This is the classic on-off test that is used to confirm that a signal is coming from a specific point in the sky. The signal also persisted for several hours, which is hard to explain with a transient source of interference like an airplane or a passing satellite. But the signal also had some puzzling features. The 982 Hz frequency is not a protected quiet band for radio astronomy. It's a frequency that is used by various terrestrial technologies, and the Doppler drift, while consistent with a planetary source, was also a bit strange. It was a simple linear drift. A real signal from a planet would have a more complex curved drift as the planet's rotation and orbit changed its velocity relative to us. The investigation was like a detective story. The team had a prime suspect, but they needed to build an airtight case. They went back and analyzed all the data from the 2019 observing run, looking for other signals that had similar characteristics. And they found some. They found a whole family of signals, all at frequencies that were multiples of a common base frequency. These look-alike signals were clearly not from space. They were a form of local radio interference. But they had the same narrow band drifting characteristics as BLC-1. This was a major red flag. So it suggested that BLC-1 might be just another member of this family of interfering signals, one that just happened to be in the right place at the right time. The final nail in the coffin came when the team was able to trace the source of the interference. They found that the signals were being generated by a piece of electronic equipment at the observatory, or possibly in the surrounding area. The specific piece of equipment was never identified, but the evidence was overwhelming. The signal was not from Proxima Centauri, it was from Earth. In 2021, the Breakthrough Listen team published 2 papers detailing their findings. They laid out the entire story of the signal, from its exciting discovery to its disappointing resolution. They concluded that BLC-1 was not a techno-signature, but rather an intriguing and as yet unidentified human-generated radio frequency interference. The story of BLC-1 is not a failure. It is a triumph of the scientific method. The team did exactly what they were supposed to do. They found an interesting signal. They subjected it to the most rigorous testing they could, and they followed the evidence to its logical conclusion, even though it was not the conclusion they had hoped for. The BLC-1 incident was a dress rehearsal. It showed that the team's detection systems and verification protocols work. They are capable of finding a faint, needle-in-a-haystack signal and distinguishing it from the overwhelming noise of our own technology. BLC-1 was not the message we were looking for, but it proved that we are ready to find it if and when it arrives. Number 2, the only signal that made us say whoa. On the night of August 15th, 1977, a radio astronomer named Jerry Eman was sitting at his kitchen table. He was a volunteer for the Big Ear Radio Telescope project at Ohio State University. His job was to go through the reams of computer printout that the telescope generated each day looking for anything unusual. The Big Ear was conducting a systematic survey of the sky, listening for narrow band signals that could be a sign of an extraterrestrial civilization. For years it had heard nothing but static. But on that night, as Eman scanned the columns of numbers and letters, he saw something that made him sit up straight. The printout showed a signal that was almost impossibly strong. The telescope measured the intensity of signals on a scale from 1 to 9. If a signal was stronger than 9, the computer would start using letters. A was for a signal 10 times stronger than the background noise. B was for 11 times stronger, and so on. The signal that Eman saw had peaked at a level designated by the letters 6E. The U represented a signal that was more than 30 times stronger than the background noise. It was a stunningly powerful burst of radio waves. The signal lasted for 72 seconds, the exact amount of time it took for the telescope's beam to sweep across a point in the sky. It was a narrowband signal at a frequency very close to the 1420 MHz hydrogen line. It had all the hallmarks of a potential artificial signal. Eman was so excited that he grabbed a red pen and circled the anomalous sequence of letters and numbers. In the margin, he wrote a single word, "Wow." The name stuck. For more than 40 years, the WOW signal has been the most famous, most intriguing, and most mysterious candidate signal in the history of SETI. It is the poster child for the search for extraterrestrial intelligence. The signal came from the direction of the constellation Sagittarius. It appeared to come from a fixed point in space. It was powerful, it was narrowband, and it was at a magic frequency. It checked all the boxes. The team at the Big Ear was ecstatic. They thought they might have found the Holy Grail. They immediately tried to find it again. They pointed the Big Ear telescope back at the same spot in the sky and listened. Nothing. They tried again the next night. Silence. Over the next few weeks and months, they and other astronomers around the world repeatedly scanned that patch of sky. They used more sensitive telescopes. They listened for longer periods. They never heard it again. The signal was a one-time event. This is the great and enduring mystery of the WOW signal. If it was a genuine beacon from an alien civilization, why did it never repeat? Over the years, dozens of theories have been proposed to explain the signal. The most mundane explanation is that it was some form of terrestrial interference. Perhaps it was a signal from a military satellite or a reflection of a ground-based broadcast off a piece of space debris. But no one has ever been able to identify a specific source that could have produced a signal with all the characteristics of the WOW signal. The signal was in a protected frequency band where transmissions are forbidden, and its 72-second duration, perfectly matching the telescope's transit time, is very hard to explain with a moving source like a satellite. Another theory is that the signal was a natural phenomenon. In 2017, a professor of astronomy proposed that the signal could have been caused by a comet. The idea was that two comets, which were not discovered until years later, were passing through the telescope's field of view at the time. The comets would have been surrounded by a large cloud of hydrogen gas. This gas cloud, when stimulated by the sun, could have produced a radio signal at the hydrogen line frequency. This theory generated a lot of headlines, but it was quickly debunked by other astronomers. They pointed out that a comet's hydrogen cloud would produce a broad signal, not the narrow band signal that was observed. And it would not be powerful enough to be detected by the Big Ear telescope. So we are left with the most extraordinary possibility. Was the WOW signal a genuine message from an extraterrestrial civilization? If so, why was it so brief? Perhaps it was a powerful wide beam signal that was just sweeping across the galaxy, and we happened to be in its path for 72 seconds. Or perhaps it was a tightly focused beam, like a laser, that was aimed at something else, and we just caught a fleeting glimpse of it. Or perhaps it was aimed at us, but the senders, for reasons of their own, only sent the message once. We may never know for sure. The Big Ear telescope was dismantled in 1998. The patch of sky where the signal originated has been studied more intensely than any other in the history of SETI. The silence has been deafening. The WOW signal remains an enigma. It is a single, tantalizing data point that hints at a universe far stranger and more wonderful than we can imagine. It is a 72-second whisper from the stars that has echoed in our imagination for a lifetime. Number 1, the silence that is the loudest signal of all. There is a question that has haunted humanity for centuries. It is a question that underlies all of our myths, our religions, and our science. It is the question of our own solitude. Are we alone in the universe? In the 20th century, we developed the tools to try and answer that question empirically. We built giant radio telescopes, massive ears that could listen to the symphony of the cosmos. We began to search for the one sound that would change everything, the sound of another mind. This search, which we call SETI, is one of the most profound scientific endeavors ever undertaken. And so far, its most significant finding has been a signal of overwhelming and profound silence. This silence is often called the Fermi paradox, named after the physicist Enrico Fermi. In 1950, during a lunch with colleagues, Fermi asked a simple question. The universe is ancient, about 13.8 billion years old. Our galaxy, the Milky Way, is home to hundreds of billions of stars. Many of these stars are much older than our sun. If life is a common occurrence, and if a certain fraction of life becomes intelligent and develops technology, then the galaxy should be teeming with civilizations. Some of them would have had a head start of millions or even billions of years. They would have had plenty of time to explore and colonize the galaxy. So Fermi asked, where is everybody? The silence that our radio telescopes have recorded is the observational evidence for the Fermi paradox. We have been listening more or less continuously for more than 60 years. We have scanned millions of stars across a wide range of frequencies. We have found a handful of tantalizing, unexplained signals like the WOW signal or BLC1. But none of them have been confirmed. None of them have been repeated. We have found no undeniable, unambiguous evidence of an extraterrestrial technology. The universe, as far as we can tell, is quiet. This great silence is a signal in itself. It is a piece of data, and it is arguably the most important piece of data we have in the search for extraterrestrial life. The question is, what does it mean? There are many possible answers to Fermi's question, many possible explanations for the silence. They range from the hopeful to the terrifying. Perhaps we are simply not listening correctly. The universe is a vast place, and the cosmic haystack of possible frequencies, locations, and signal types is unimaginably large. We have only searched a tiny fraction of it. It's as if we have scooped a single glass of water from all the world's oceans and, finding no fish, concluded that the oceans are empty. Maybe the aliens are out there, but they are communicating in a way we can't detect using technologies like neutrinos or gravitational waves that are far beyond our current capabilities. Or perhaps they are deliberately not communicating. The zoo hypothesis suggests that advanced civilizations may be aware of us, but have chosen to observe us from a distance without interfering, treating us as a nature preserve. Or, in a more sinister version, perhaps the galaxy is a dark forest. In a dark forest, you don't shout because you don't know who or what might hear you. Any civilization that reveals its presence risks being destroyed by a more advanced and possibly hostile competitor. In this scenario, the silence is a sign of fear. The smart civilizations are the ones that are quiet. And then there is the most unsettling possibility. Perhaps the silence is a sign that we are, for all practical purposes, alone. Perhaps the emergence of intelligent technological life is an incredibly rare event. Perhaps there is a great filter, a series of evolutionary or technological hurdles that are so difficult to overcome that almost no species ever makes it through. The filter could be behind us, maybe the emergence of life itself, or the jump from single-celled to multi-celled organisms is the incredibly rare step. If so, we are one of the lucky few who have made it through. But the filter could also be in front of us. Perhaps every advanced civilization eventually discovers a technology like nuclear weapons or artificial intelligence that leads to its own destruction. In this case, the silence is a warning. It is the sound of a galaxy full of dead civilization. The Great Silence is the loudest and most persistent signal we have ever received from space. It is a signal that speaks to our deepest hopes and fears. It forces us to confront our own place in the cosmos. Are we the first, the last, or just one of many? Are we living in a universe that is full of potential friends, or one that is a vast and empty tomb? We don't know the answer. All we can do is keep listening. The search for a single, anomalous signal is also a mapping of the background silence. Each new survey that finds nothing but static adds another layer of depth and mystery to that silence. And with each year that passes, the quiet from the stars grows a little louder.